In this lecture, we're going to talk about solving first-order ordinary differential equations by using substitution. So we're going to focus in on three different types of equations in this section. The first is called a homogeneous equation. The second is Bernoulli's equation. And the third are equations of the form dy dx equals some function f of the linear combination ax plus by plus c. Now, for all three types of equations, we can use an appropriate substitution factor, and then the equations are going to be solved by using either separation of variables or by using an integrating factor. So let's start with homogeneous functions. By definition, a function f of xy is said to be homogeneous if of degree alpha if f evaluated at tx ty can be simplified to be t to the alpha times f of xy. So for example, if we have the function f of xy equals x squared plus 3xy, and we replace x and y with tx and ty, we would get tx squared plus 3 times tx times ty. If we simplify that, that'd be t squared x squared plus 3t squared xy. And we can factor a t squared out of both terms to rewrite this as t squared times x squared plus 3xy. Now notice this is t squared times our original function, so t squared times f, and so this satisfies the definition, and it is going to be a homogeneous function of degree 2. All right, so now that we know how to show that a function is homogeneous, let's translate that to equations. So in differential equations, a first-order differential equation written in differential form, m of xy dx plus n of xy dy equals 0, will be a homogeneous differential equation if both functions m and n are homogeneous functions of the same degree. So if we check m and n and show that we can rewrite them and show that they're homogeneous with the same degree, then that'll make this a homogeneous differential equation. If we have a homogeneous differential equation, we can use the following steps to solve it. First, we're going to use an appropriate substitution factor. We're either going to use y equals u times x and dy equals u dx plus x du, or we can use x equals vy, and so dx would equal v dy plus y dv. Once we've chosen our substitution factor, we'll plug that in and we'll simplify our equation. And then the simplified equation can be solved using separation of variables. So let's look at an example. We have y dx equals 2 times x plus y dy. The first thing we want to do is we want to write this in differential form, so we want everything to be on the same side of the equation. So we'll subtract the 2x plus y dy to the other side. So y dx minus 2 times x plus y dy equals 0. Next, we'll check to see that this is a homogeneous equation. So m is equal to y, and n is equal to negative 2 times x plus y. If we evaluate m and n at tx ty, we would get m of tx ty equals t times y. So that's t times m. So this shows that m is homogeneous of degree 1. And if we evaluate n at tx ty, we get negative 2 times tx plus ty. We can factor a t out of that. So this is t times negative 2 times x plus y. And again, that's going to be t times our original function n. So this shows that n is also homogeneous of degree 1. So since both are homogeneous of degree 1, that means that our overall differential equation will be a homogeneous differential equation. To solve our differential equation, we'll use one of our substitution factors. For this one, we're going to let x equal vy, and then dx will equal v dy plus y dv. We're going to substitute these factors into our differential equation. So we had y dx equals 2 times x plus y dy. If we make our substitutions, we'll get y times v dy plus y dv equals 2 times vy plus y dy. We're going to simplify by multiplying through to remove our parentheses. And if we do that, we get vy dy plus y squared dv on the left-hand side. And we get 2vy dy plus 2y dy on the right-hand side. Now we want to work on separating our variables. So we're going to move all of the terms that have dy to the right-hand side. So we're going to subtract vy dy from both sides. And so 2 is going to become just vy dy. So we have y squared dv equals vy dy plus 2y dy. On the right-hand side, we can factor out a y dy. So we get y squared dv equals y times v plus 2 dy. And now we can separate our variables. We can move all of our v terms to the left-hand side with dv, and we'll move our y terms to the right-hand side with dy. And if we do that, we get dv over v plus 2 equals y over y squared dy. Now that our variables are separated, we can integrate both sides. So dv over v plus 2 equals 1 over. Integrating both sides, we'll get the integral of dv over v plus 2 equals the integral of 1 over y dy. If we evaluate those integrals, we'll get the natural log of v plus 2 equals the natural log of y plus c. Now remember, our original problem didn't have v's in it. It had x's and y's. So at some point we need to substitute back. So if x was vy, then that means v has to be x divided by y. So let's go ahead and make that substitution. That means we have the natural log of x over y plus 2 equals the natural log of y plus c. We're going to simplify this a little bit. So to get rid of the natural log on both sides, we'll use the exponential function. So e raised to the natural log of x over y plus 2 equals e raised to the natural log of y plus c. On the left-hand side, the e and the natural log will cancel out. On the right-hand side, we'll rewrite this as e to the natural log of y times e to the c. And e to the c is just a constant, so we can rename that. So we wind up with x over y plus 2 equals c1y, where c1 was that e to the c we talked about a moment ago. All right, the final thing we're going to do here is we're going to multiply everything by y to get rid of that fraction. And so we're going to get x plus 2y equals c1y squared. And this will be an implicit solution to the differential equation. Let's look at a second example. So this time it says solve the following homogeneous equation. X plus y times dx minus x times dy equals 0. Since they told us that it's homogeneous this time, we're not going to worry about showing that it's homogeneous because we already know they told us it was. So we're just going to solve this. The first thing we do is we choose our appropriate substitution factor. So if we look at the two terms here, we have x plus y times dx, and we have x times dy. X times dy is the simpler term, so I want to choose the substitution that's going to involve dy. So if I do that, I'm going to let y equal ux, and dy equal u dx plus x du. We apply these substitutions, so that gives us x plus ux times dx minus x times u dx plus x du is equal to 0. After we've done our substitution, we're going to simplify by distributing and getting rid of our parentheses. So the first term, we're going to get x dx plus ux dx. And from our second term, we'll get negative xu dx minus x squared du. All right, if we look at these two terms in the middle, ux dx and negative xu dx, those are the same thing, so they'll cancel each other out. So we wind up with x dx minus x squared du equals 0. Now we're ready to solve this by separation of variables. We want to separate our dx and our du. So we'll add x squared du to the right-hand side. So we get x dx equals x squared du. We'll divide both sides by x squared. So 1 over x dx equals du. And now we have successfully separated our variables. So with our variables separated, we can integrate both sides of the equation. The integral of 1 over x dx equals the integral of du. So the natural log of x plus c is equal to u. Again, we didn't have u's as our original variable, so we need to transform that back. If we started with y equals u times x, that means u has to be y over x. So our problem now is the natural log of x plus c equals y over x. And if I want to get y by itself, I'll multiply everything by x, and I get x times the natural log of x plus c times x is equal to y. And so that'll be a solution to this differential equation. The next type of problem that we'll see in this section is called Bernoulli's equation. So Bernoulli's equation is an ODE of the form dy dx plus p of xy equals f of x times y to the n. So this looks a little bit like a linear equation, except on the right-hand side we're multiplying by y raised to some power. All right, if we have Bernoulli's equation, we're going to use the substitution factor u equals y to the 1 minus n. And if we apply that substitution factor, then the equation is going to be reduced to a first-order equation, which we can solve with an integrating factor. So let's do an example of a Bernoulli equation. Here we have dy dx minus y equals e to the x times y squared. So we can see that this follows the form of a Bernoulli equation. It looks like it's linear, but on the right-hand side we have this y to the 2 power. So n is going to equal 2 in this problem. And that means that we'll start with the substitution factor, u equals y to the 1 minus n. So u is y to the 1 minus 2, which will be y to the negative 1. Now this substitution isn't very helpful at the moment because we don't have any u's. We don't have any u's in our problem, and we don't have any y to the minus 1's either. So I can't use this for a direct substitution. So what I'm going to do is I'm going to take this substitution factor, u equals y to the minus 1, and I'm going to solve it for y. So if u equals y to the minus 1, then that means y has to equal u to the minus 1. And so this I can use for a direct substitution. I can plug u to the minus 1 in for both of these y's. I also need an expression for dy dx. So if I know what y is, I can find dy dx by taking the derivative. So the derivative of y would be negative u to the negative 2 times du dx. Now I have an expression for dy dx and for y. We're going to plug those expressions in, so we're going to substitute. And our problem is going to become negative u to the negative 2 times du dx minus u to the negative 1 equals e to the x times u to the minus 1 squared. So this is a linear equation, or will be a linear equation, and so the way that we solve that is by putting it in standard form first. So we're going to divide everything by the leading coefficient, negative u to the negative 2. That'll put us in standard form. On the first term, negative u to the negative 2 will just cancel out, so we get du dx. On the second term, if we divide a negative by a negative, it becomes a positive, and u to the negative 1 divided by u to the negative 2 just gives us u. On the right-hand side, if we divide a positive by a negative, it becomes negative. E to the x will stay the same. And then we have u to the minus 2 divided by u to the minus 2, so those will cancel out. So the standard form of our equation is going to be du dx plus u equals negative e to the x. Now that this is in standard form, we can identify our coefficient of our dependent variable and use that to find our integrating factor. So p of x is going to equal 1, so that's a 1 right there, and that means that our integrating factor will be e raised to the integral of 1 dx, or e to the x. We'll multiply the standard form by that integrating factor, so we get e to the x times du dx plus e to the x times u equals negative e to the x times e to the x. And then we're going to simplify. So remember, when we work these first order linear problems using an integrating factor, the left-hand side is always going to simplify to be the derivative of your integrating factor, so that's e to the x in this problem, times your dependent variable, which is going to be u. So we get the derivative of e to the x times u, and on the other side, e to the x times e to the x will give us e to the 2x. And so since we've simplified, now we can integrate both sides. So the integral of the derivative of e to the x times u with respect to x will equal the integral of integral of negative e to the 2x dx. Taking those integrals, we're going to get e to the x times u equals negative e to the 2x over 2 plus c. We're going to solve this equation for u, so we'll divide everything by e to the x. That's going to give us u equals negative e to the x over 2 plus c times e to the minus x. And then our final step, again, is to go back to our original variables. Remember, there wasn't a u in our original problem. So we need to take this and we need to transform it back so that it has our original variables. So at the very beginning, we said u was y to the minus 1, so we'll just apply that substitution. So we get y to the minus 1 equals negative e to the x over 2 plus c times e to the minus x. And that'll be the solution to this Bernoulli equation. Let's look at another example of a Bernoulli equation. So this time we have 3 times 1 plus t squared dy dt equals 2ty times y cubed minus 1. The first thing that we want to do is we want to manipulate this so that it looks like it's in the form of a Bernoulli equation. We're going to go ahead and distribute the right-hand side. So 3 times 1 plus t squared dy dt equals 2t times y to the 4th minus 2t times y. And we're going to move the negative 2ty term to the left-hand side, so we'll add it over there. So 3 times 1 plus t squared times dy dt plus 2ty equals 2ty to the 4th. So now we're in the form of a Bernoulli equation. Well, excuse me, we're not quite there yet. We need to divide by this leading term. So a Bernoulli equation should have 1 as its leading coefficient. So we need to divide by 3 times 1 plus t squared. So dy dt plus 2t over 3 times 1 plus t squared times y equals 2t over 3 times 1 plus t squared times y to the 4th. Now we're in the form of our Bernoulli equation. The right-hand side, we have an n value of 4. So that means we're going to let u equal y to the 1 minus 4, or y to the negative 3 power. Again, this isn't very useful to us at the moment because we don't have any u's in our problem, and we don't see y to the negative 3 anywhere in our problem. So we're going to solve this substitution for y. If u equals y to the negative 3, that means y has to be u to the negative 1/3. And if y is u to the negative 1/3, we can take the derivative. So dy dt will be negative 1/3 u to the negative 4/3 times du dt. We'll apply those two substitutions, and now our problem becomes negative 1/3 u to the negative 4/3 times du dt plus 2t over 3 times 1 plus t squared times u to the negative 1/3 equals 2t over 3 times 1 plus t squared times u to the negative 1/3 to the 4th power. We'll put this in standard form by dividing everything by negative 1/3 u to the negative 4/3. In the first term, that'll cancel out. We'll get du dt. In the second term, if we divide a positive by a negative, we get a negative. The 1/3 and the 1/3 cancel out, so we're left with 2t over 1 plus t squared. And u to the negative 1/3 divided by u to the negative 4/3 will simplify to be u to the 1 power. Similarly, on the right-hand side, a positive divided by negative gives us a negative. Those 1/3 will cancel each other out, so we're left with 2t over 1 plus t squared. Here we have u to the negative 4/3 if we put that together, and if I divide by u to the negative 4/3, it'll cancel out. So I'm left with du dt minus 2t over 1 plus t squared u equals negative 2t over 1 plus t squared. Now that this is in standard form, we can identify our integrating factor. So p of t is negative 2t over 1 plus t squared. That means our integrating factor will be e raised to the integral of negative 2t over 1 plus t squared. So if we use substitution factor, let's call those w's. So if w equals 1 plus t squared, then dw would equal 2t dt. That means we have e raised to the integral of negative 1 over w dw. And so that's going to be e to the negative natural log of w, or e to the negative natural log of 1 plus t squared. We can move the negative sign up into the exponent inside the logarithm, and then the e and the natural log will cancel out, so our integrating factor will be 1 over 1 plus t squared. We're going to multiply everything by this integrating factor in our standard form, and that's going to give us 1 over t squared times du dt, minus 1 over t squared times 2t over 1 plus t squared equals a negative 2t over 1 plus t squared times 1 over 1 plus t squared. We'll simplify this. So the left-hand side again will simplify to be the derivative of our integrating factor, 1 over 1 plus t squared, times our dependent variable u. And on the right-hand side, we'll get negative 2t over 1 plus t squared. We integrate both sides of that. And so that's going to give us 1 over 1 plus t squared times u equals, on the other side we'll use substitution again, where w is 1 plus t squared, and so dw would be 2t times dt. And so when we integrate that, we would wind up with 1 over 1 plus t squared plus c. Final steps are to multiply by 1 plus t squared to get u by itself. So u is going to be 1 plus c times 1 plus t squared. And then finally, u wasn't one of our original variables, so we need to substitute back. So at the very beginning, we said u was equal to y to the negative 3 power. So y to the negative 3 will equal 1 plus c times 1 plus t squared. And that'll be the solution to this second Bernoulli equation. All right, the final type of problem that we're going to see in this section deals with reduction to separation of variables. If we see a differential equation of the form dy dx equals f of ax plus by plus c, it can often be reduced to a separable equation if we use the substitution factor u equals ax plus by plus c. For our first example, we have dy dx equals 1 minus x minus y over x plus y. I want to choose a substitution factor that has the form ax plus by plus c, and I see both x and y in the numerator and the denominator, but the signs are different. So I'm going to start by factoring the negative sign out from this numerator. That's going to give me dy dx equals 1 minus x plus y over x plus y. Now that I have the same term in both the numerator and denominator, I'm going to let that be my substitution factor. So let's let u equal x plus y. If u equals x plus y, I can take the derivative, so du dx would equal 1 plus dy dx, and I can solve that for dy dx to get myself another substitution factor. So dy dx would be du dx minus 1. So I can take this and plug it in for dy dx. If I apply my substitutions, dy dx becomes du dx minus 1. The right-hand side, I get 1 minus u divided by u. We're going to separate our variables. So first I'm going to add 1 to both sides. So du dx equals 1 minus u over u plus 1. In order to add these terms together, I would need a common denominator. So I can rewrite 1 as u over u. And then when I add these, minus u and plus u in the numerator will cancel out. So we get du dx equals 1 over u. Now we can separate our variables. We'll multiply u by both sides, and we'll multiply dx to both sides. So we wind up with u du equals dx. Now our variables are separated, so we'll integrate both sides. So the integral of u du equals the integral of dx. So u squared over 2 equals x plus c. And just like with our previous problems, our final step here is to go back to our original variables. Remember, we didn't have a u in our problem, so we can't have a u in our answer. So we're going to go ahead and substitute back u is equal to x plus y. So that gives us x plus y squared over 2 equals x plus c. So that'll be an implicit solution. We can multiply both sides by 2 to remove the fraction and make it look a little prettier. So x plus y squared equals 2x plus some constant c1. That can be our solution. All right, for our final example, we have dy dx equals 1 plus e to the y minus x plus 5. So we notice inside the e function, inside the exponential, we have y minus x plus 5. That's of the form ax plus by plus c. So let's let that be our substitution. Let u equal y minus x plus 5. And just like we did before, we're going to take the derivative of that. So du dx equals dy dx minus 1. And we'll solve that for dy dx. So dy dx equals du dx plus 1. We can take this and we can substitute it in for dy dx. So applying our substitutions, we get du dx plus 1 equals 1 plus e to the u. We'll subtract 1 from both sides. So du dx equals e to the u. And now we can separate our variables. So we'll put all of our u's on the left-hand side by dividing by e to the u. We'll put our x's on the right-hand side by multiplying by dx. So du over e to the u, or e to the minus u du, is equal to dx. Now that our variables are separated, we can integrate both sides. So the integral of e to the negative u du equals the integral of dx. So negative e to the negative u equals x plus c. And again, we resubstitute. So negative e to the negative y minus x plus 5 equals x plus c. And that'll be an implicit solution to our differential equation.